most welcome June edition of Renewables Technologies. So a few ground rules. We shall use the chat space for any communications that you wish to make. We shall also have a dedicated question and answer session at the end of the webinar, where you'll have an opportunity to submit your questions to the guest speaker. In case you are comfortable, you can turn on your video. Would really like to see you. So in the meantime, we could kindly use the chat space to just introduce ourselves. So you can tell us your name, profession, if you're a student, your course, perhaps university or secondary school, and also the country you're joining from or the place you're joining from. Yes. I would also like to welcome our team leader to just say something to us before we can kickstart the webinar. Shalom, you're most welcome.
Thank you so much, Enoch. Thank you so much, everyone, for joining once again. This is the June edition, and I'm super excited to be learning along with everyone. So you're welcome. Thank you so much, Enoch. Over to you.
All right, that is Shalom. So we'll start with the speaker introduction, then we'll have an overview of the topic. Then we shall have the guest speaker coming on to deliberate. So our guest speaker for this edition, as we all know,
Enoch, are you still there? Enoch, can you still hear me? Okay,
yes,
everyone.
sorry
Okay.
for that. Sorry for that. The network had skipped a bit. So I was introducing our guest speaker for our June edition. So our guest speaker is Dr. Isah Yakub Mohammad, who is a distinguished senior lecturer in chemical engineering at Abubakar Tafa Balewa University in Nigeria. Our guest speaker completed his doctorate in chemical engineering in 2017 at the University of Nottingham. His thesis was on biofuel production from Nipah grass and also holds different postdoctoral fellowships. Some of his key achievements are publishing over 58 peer-reviewed papers. You can check out his details or publications on Google Scholar. His H index is 22. You can also check out his publications on Scopus. He has also secured various grants whose net worth is 250 million plus in Naira. So, ladies and gentlemen, today we are joined by a very distinguished guest whose profile I've just read. All right, so today's, Shalom has displayed it for us. So today's topic is designing energy-rich fuels using biomass and plastic precursors. One may ask, if you can view me, I have a plastic bottle with me here. So today we are going to have a conversation on how to produce fuel from this plastic waste.
Okay, I'll take it a bit from here before Enoch joins back.
Yeah.
Okay, he's here again.
Our guest speakers joined.
Let me see. Okay, before our guest speaker joins, yes, Enoch, please go ahead for your presentation before our guest speaker joins.
All right. So tonight's topic, as I was introducing, is on designing energy fuels from plastics. As you can see with me, I have a plastic bottle here. So tonight we are going to have a conversation on how we turn this into valuable fuels. So according to the International Energy Agency, that is IEA, a renowned global organization that does research in energy, it suggests that says that 60% of the total plastic solid waste that is consumed by humans ends up in landfills, thereby contributing to waste. And because these plastics do not biodegrade, it then leads to things like loss of soil fertility and etc. But at the same time, we are aware that transportation as a sector contributes to a third of the global greenhouse gas emissions. So tonight's conversation is on how we are able to leverage on these two seeming challenges, how we are able to convert this plastic waste into the fuel that can be used to power sectors such as transportation and also industry. So ladies and gentlemen, join me as we welcome our guest speaker who will further our conversation on tonight's topic. Dr. Isah Mohammad, you're most welcome. Thank you.
Oh, thank you so much. My sincere apologies. I think we're experiencing a little bit of hitch trying to get the facilitator for today, but he's currently joining the call. Just a little moment. And while we are waiting for the facilitator to join the call, please let's feel free to introduce ourselves in the chat box. Your name. I see a lot of people have already started introducing themselves. Welcome, Abdul Gaya, a graduate of economics from Nigeria. We're happy to have you here. Welcome, Praise. Please feel free to use the chat box to introduce yourself, tell us your name, where you're joining in from, and of course, your profession, if you feel free to share that with us. Of course, our moderator is joining in from Uganda. You can see we are a diverse community here. So in the chat box, just your name, your profession, and where you're joining us from. Oh, welcome, Andrew. Great to see you again. Um, Hi, Brian. I know, right? Congratulations on the gold winner award. The okay, I see our facilitator is here, so I wouldn't go ahead to introduce everyone again. But everyone from Gulu University, welcome. Thank you for joining us. Welcome, Jefta. Um, and I'll pass it on to our esteemed facilitator for today, Dr. Isah. It's a pleasure to have you join us. Please proceed with your presentation. Thank you so much.
Thank you so very much. The organizer, the Energy Awards, and Praise. Good to have you together here this afternoon. And those of you that have joined, you're welcome to this short presentation. Before I proceed, I would like to share my slide with you so that you can follow through what we'll be talking. Is that okay with us? Hello?
Yes.
Yeah, good. Great. So let me share my slide. Great. Can you see my slide now?
Yes, it can.
Thank you. Thank you. All right. Thank you once again for joining this presentation. The title of the presentation, the Green Fuel Revolution, Designing Energy-Rich Fuel Using Biomass and Plastic Precursor. So I'll try as much as possible to be able to carry us through. And then we also, in the course of this presentation, we're going to present some sort of case studies that were carried out in the Material Energy Laboratory here in Nigeria. So I hope you enjoy it. Yeah, so this is it. Why do we even have to look for what we call the green fuels, and what necessitates the need for the alternatives? So as I said, I'm looking at Nigeria, a case study in Nigeria, where you have about more than 140 million people have no access to clean cooking fuel and cooking technology. And then you can see from the slide, you see the traditional way of cooking, you can see smoke everywhere. Burning of firewood would generate a lot of what you call gases that are not that have health consequences on the human, that the user, and also have negative impact on the environment. So according to statistics, you can see 7 out of 10 use bad solid fuel for cooking, which emit large amount of health damaging airborne pollutant. All these are borne out from the what you call the continuous increase in the price of the cooking gas. And the larger percentage of population have resorted into using the cheapest and the cheapest and the easily accessible fuel, which is generally gotten from the cutting down trees. And then if we allow this trend to continue, what the negative impact on the environment is, it cannot be imagined. And while we continue to allow such a thing to happen, you will see that there will be what we call desert encroachment, and the most in African countries, you will see that trees, when they cut the trees, they are not replaced, and then the deforestation set in, and when it is not abated, you will see that a lot of challenges will come in. And we want to have the world or the nation or a country whereby our present activity will not have negative impact on the future generations. So this is the problem we're trying to solve by coming up with alternatives. Yeah, and what are these alternatives? We come up with an objective to see that we can develop a waste-based low-carbon alternative fuel that is environmentally friendly and can be utilized to meet up with our domestic energy needs, and also that will support the sustainable living. So specific objectives of this is to harness the potential. So like we've seen in the previous slide, the main source of fuel is firewood, while in this approach we adopted is the waste. And these wastes are non-food, non-feed biomass material that can easily be converted into alternative or fuel precursor to support sustainable living and by meeting the domestic energy requirement. So these are some of the objectives to demonstrate also the combustion technology of solid fuel derived from waste as a clean alternative to cooking gas, and to channel the energy drive from the waste conversion towards modernization of domestic cooking and heating systems, and also support sustainable living. Now, having stated out these clear objectives, we can see the first thing is to be able to come up. Since people, they already have what we call the domestic heating system that is compatible with the solid fuel, All right, we say, okay, let's come up with an alternative to which is production of a biocoal from the biomass. And then this is the conceptual process that we developed in Material Energy Laboratory. We've got the municipal solid waste or low-grade, low-value agro residue, and then the stream divider here, if you can see the slide carefully, where we have the stream divider here. And on this side, we've got the torrefaction reactor, whereby we convert this biomass material to a more energy-dense material. And while doing this, we take cognizance of what energy intensification by when the volatiles are released, they pass through the condenser, and then we try to use the cooler to be able to get the volatiles, some that are condensables. And from there, we can have our non-condensable vented, which possibly has got some sort of chemicals in it, which in these scrubbers are able to travel in, which can be further processed into valuable materials. And then for the torrefied biomass, we have it here. And then from the low, the fraction here, which undergo what you call lignin extraction, which is another energy, energy stream that can precursor that can also be utilized in the downstream system to generate fuels. Okay, so after the lignin extraction, we've got the residue combined with torrefied biomass, blend them, and then we carry out what you call thermal leaching to be able to demineralize in such a way that we can have a precursor, biocoal precursor. And then after the filtration here, the leachate. After the thermal leaching, you've got the leachate here, filtration takes place here, and then we have the residue or the fine particulate to put together with the biocoal precursor. And then from this process here, you can see the lignin extraction. We use lignin as a binder here, so that everything we're using here is non-food, non-feed, all from biomass. And then we blend it at a specific ratio, and then we briquette and to get our biocoal. So, and having achieved that, we also look at what are other streams, product streams or material streams that are available that we can be able to utilize to be able to give to additional revenue stream in the cost of production. Here we said the leachate, which is alkaline in nature. It can be charged into the lignin extraction reactor. And after that, lignin is extracted, which we have seen here, the application. We filter the leachate, and then here we have the black liquor, which we precipitate, centrifuge, undergo centrifugation to be able to get the lignin out, and that's the binder. The supernatant here, together with the alkaline phase here, put together, can also be reutilized in the downstream, so that we can recover some sort of salts that can be utilized conveniently for other consumer products. So this is just an overview of the conceptual process of producing the biocoal directly from biomass. Now, the next slide you see, we try to say, okay, if you want to haven't conceptualized the entire process, what can we do to be able to know how viable the entire process is all about? Then we decided to implement it in Aspen Plus to see what are the indicators that we can be able to guarantee us that yes, this venture is profitable and environmental sustainable. So this is now the implementation of the process flow diagram. The earlier slide was developed using Microsoft Visio, and here we have the process flow sheet now in the Aspen environment, where we have our torrefied reactor, as we rightly seen there, and then we have the condenser connected to the coolant, and then we have torrefied biomass and residue. This is the lignin extraction reactor. And then we put them together here. We have hydrothermal leaching. From the hydrothermal leaching with the fine particulate, we have the lignin extracted, and then there's the binder, and then we have the biocoal. And also, as we rightly said in the earlier slide, we've got to see the recovery of other salts that probably have what you call downstream application. So on that, we move further to see how we can design the reactor, fabricate them, and to be able to see using the local technology. Here you have the 3D diagram of the reactor that we designed here in Material Energy Laboratory. to be able to see. Look at from this side, this left-hand side, you can see is the heating element. Here you've got the quenchants, and then we have the what you call the scrubbers here before the venting. Yeah, so this reactor is of particular interest for us because it has ability to carry out in situ demineralization. One of the challenges where we come up with this project is for us to be able to see how we can come up with ashless and smokeless biocoal, because the challenge is when during the application of this coal, particularly those that are available in the market today, there is none that you can tell that when after subjected to combustion, it will release, it won't give a substantial amount of the ash, which is generally a problem, which hinders the application of this so-called biocoal or the charcoal in the market in indoor application. So these are the challenges that are currently delving what you call the application of the solid fuel. So in our own solution, we come up to one single reactor. Traditionally, what they do here after the torrefaction, the demineralization is another compartment. Here we have everything put together. In this reactor system, after the torrefaction, there is what you call demineralization, hot demineralization, where with this system we charge in the water to be able to demineralize when the torrefied biomass is still red hot. And then from there, you see the inorganic material that normally that result to the formation of the ash material already excited, and then by the time you add water into it, it's quenched directly and leach into the water, and then you've got that water which is rich in alkaline metal, which can be utilized for the lignin extraction. So this is 2-in-1 reactor system that is able to solve our problem. And then after that, we've got to see this is the practical fabrication. This is a typical, the physical picture of what you call picture of the reactor. And this is it. This is the reactor itself with the heating element. So with this system, we've been able to come up with biocoal that is, to some extent has got less ash production. But our main target is to be able to produce a biocoal that is ashless and smokeless. For the smokeless, we have achieved that. Yeah. So here you have the biomass, and this is the coal we have produced, and this is the typical biomass from Chiano shell. Chiano shell. That's in the course of the initial presentation, I've mentioned that we are focusing on non-food, non-feed biomass, so that we don't have issues with animal feed, or we don't come up with problems of competition with other biomass users. So here, Chiano shell is one of the what you call residue in the shea butter processing. And this is particular to West Africa because the shea belt is within the West African countries, and this component of the material are generally regarded as what? Waste. It has no value. Most of the valorization techniques are just open burning. And open burning is another way of also contaminating the environment. So this material, it's non-feed, it's non-food, non-feed, and it cannot be used just as completely waste. And that's we pick this and then we pulverize it, and this is a typical Chiano shell. And then we subject it to torrefaction, and then at the end of the day, we come out with what torrefied biomass, and then we use also a residue, which is cassava peel. Cassava peel, particularly those that are from bitter origin, that is high cyanide content cassava, in which these peels are no longer used for animal feed because of the high level of cyanide. Because when they consume it, it becomes a problem that can even lead to death of animals. So by so doing, that aspect of the cassava processing is left underutilized. So we say, okay, fine. Since this is the problem, we can selectively extract the cassava, the starch in it, and then use it as a binder and to produce our coal. As you can see here, this is coal that's produced in the Material and Energy Laboratory to serve as an alternative to the charcoal that is being used for domestic to meet the domestic energy need. So you can see the top here, you've got some sort of like brown coal, and this in our technology. Can you hear me, please?
Okay, we can hear you now.
Oh, sorry about that. Okay. So what I'm saying is this. If you look at this right-hand side, you've got to see like a brown coal in it. And this brown coal in our technology that you will see in the next slide is self-ignition system that you don't need to, because traditionally in most African countries, what they do is to be able to look for external ignition source to be able to light up the coal. In our solution, we come up with something that is the brown coal, which will serve as a contact point with the igniter within the system to first of all ignite the fuel and then circulate same to the entire the coal in the chamber. And so that's why you see and this is produced from the millet shaft. Millet shaft also rarely used. They're mostly also subjected to open burning after the cultivation of that millet. And this is one of the aspects that's is very difficult for animals to like digest unless you subject it to some sort of treatment. Otherwise, it's also regarded as a waste in most African countries. And that's why it's okay. Let's utilize this material as one of the component of biocoal that will serve as a point of ignition to other coal, so that the system can completely be ignited without external addition of ignition source of what they call ignition to the fuel, because most of the people utilize the plastics and polythene bags to be able to serve as input energy before the coal can get fired. So in our solution, it's all in one. You have the self-ignition system, you have the coal that is ashless, you have the coal that is smokeless, and then with this, we have the system, the technology that fires this coal with some sort of what you call self-ignition, and then you have a complete solution. And in this next slide, you can see the types of prototype we have developed from the POC, that is proof of concept. We have come up with different scenarios, different systems to be able to see that while we are doing the cooking, we should be able to also save some energy that will support additional or some sort of application, even after the cooking. Yeah, you've got to see this one here is one of the self-ignition system and electricity generator that you can utilize in either for domestic use or for HoReCa, hotel, restaurants, and catering, areas where people can be able to utilize the system with the coal put together to be after firing or during the cooking, the energy is utilized efficiently such that the excess heat is transformed into electricity. So two pathways are involved here. If you can look very clearly, you can see that there are some steam lines in it. These steam lines, water, you can see down here, there's pump that pump water throughout these steam lines to generate steam, so that there are micro turbine here underneath that can generate some electricity, which can be stored for the application. The second one is thermoelectric generator. In the surface here, if you can see, this surface here is to be during the cooking, you can see it's going to be very hot. And then from there, the heat energy is transformed via the transducer into electricity. Can you hear me? Are we together?
Yes, we're together.
Very well. Okay. So here, if you can see here, some transducers which take thermoelectric generator, built inside with contacts in the surface. This because during the application, this place is going to be very red hot, and then from there, the energy is the heat is converted to electricity, and then that can be used for further application. As you can see, this is a dual deck. We have the dual is a single deck, and this is a dual deck. As you can see, where you can put in where the energy can be tapped for external application. And this is a POC, proof of concept, which we have fabricated practically, and this is what you see here. Okay. Now, having demonstrated all these activities cannot be explained in one what do you call a talk like this. And subsequently, we will be able to come up with maybe in the next edition of this Renew Tech, so that we can be able to demonstrate other some sort of energy carriers that we have developed from our biofuel system. One concept, many solutions have emerged from this particular project. And then we couldn't have done it well without the the support of our esteemed students and researchers that we have in material and energy laboratory.
But when I try registering again, like,
can you hear me?
Yes, sir. Sound and
You can
clear.
see, as you can see
Can hear
here.
you.
Yeah, these are the cohort, the first cohort, because I think I have to make this known. Material Energy Laboratory was established in 2022. And these are the first set of graduates that we have trained in terms of waste to energy technology. By now, with all of these, we have done projects from one waste stream to energy precursor, or the full energy stream, which have been evaluated to be able to, let's see how we can scale that up for commercial application. And this candidates now in different what we call in field of endeavor. Some of them have acquired some sort of what you call additional purchase some sort of tend to go into acquiring additional qualification. Some are currently undergoing some national service, because the policy in Nigeria, where after graduation you have to do 1 year mandatory national service. So this is the next set of people that are currently in the Material Energy Laboratory that are still undergoing training. Most of them are first year, that is undergrad, the final year students who are undertaking their projects, and we've got a couple of master students and core members serving the Material and Energy Laboratory. From my right here, you can see here, this is one of our best students as well, which has with CGPA of 4.67. Last semester, she has got 5.0 in their GPA. And this is a core member currently serving with us. These are 411 students who are doing industrial attachment here. This is a colleague. This is now the master student who is currently progressing for PhD program in chemical engineering. And we have got, this is also a core member. This core member is finished from Ebonyi State University, Abakaliki, Imperial University Abakaliki in chemical engineering. So without these gentlemen and ladies, we wouldn't have achieved what we have achieved. And we hope to collaborate more with more people so that we can make the world great again. Thank you so very much for listening.
All right. Thank you very much, Dr. Isah Yakub, for that wonderful presentation. Just a follow-up question on the characteristics of the biocoal that
Right.
you are producing. Am I audible?
Very well.
All right. Yes, I was saying just a follow-up question on the characteristics of the biocoal
Right.
that you're producing. You made mention of the fact that they are smokeless and ashless. What is that specific material that you leverage on to ensure that this product does not produce smoke when it is ignited?
All right. Thank you so very much. Can I respond directly, right?
Yeah.
Okay. Thank you so very much. When we said something is smokeless, during combustion generally, the one thing that must be clear is the theoretical air requirement. If the theoretical air requirement is not met, you are likely to have incomplete combustion. And when that happens, you've got to see that in your gas streams, you've got to see some black smoke coming in, which are component of carbon monoxide, carbon dioxide. Rather than having complete carbon dioxide, you've got to see some smoke coming in, black smoke, which are as a result of incomplete combustion. What we have in our own system here, if you can see very clearly, we have what you call a system that allow variable firing rates of the stove we've got. What does that mean is if the natural drag is not enough to have a smokeless to effect the full combustion, it's supported by a fan that will be able to support the system with additional air requirement to be able to overcome the theoretical requirement and also have excess air within the system so that it can effect what we call the complete combustion. And when that happens, you don't see some sort of smoke coming up again. You see the red glowing coal, and that is giving you the energy that is required, that is needed for the domestic activity. That is on one hand. On the second hand, to be able to see that it's ashless, we have what we call ultrasonic system that enable us at specific conditions which have been optimized to be able to give us to demineralize the ash forming element that hitherto will form the ash. So by
Doctor, I think we lost you. Shalom, am I audible?
Yes, I also do not hear him.
Okay. So in the meantime, in case you have any questions, feel free to use the chat space. I see Praise is active. We'll wait for Doctor to work on his connectivity.
Oh yes, I think he's out of the call, but he'll be joining back soon. And I just wanted to follow that up because I saw innovation in the bioenergy space. Usually I would see cook stoves without the support of electricity, in the same components, but it's amazing seeing that he designed systems that do not only provide clean cooking gas, but electricity at the same time, like in small modular form. So I think that's one of the key takeaway for me from what innovation that doctor is doing in his lab.
Okay, sorry
I think
about the interruption. Yeah.
Yes, he's back.
Yeah. So
Right.
what about the answer I've given so far? Is that okay? Is that the question
Yes.
correctly answered?
Yes, yes.
All right. Thank you so very much.
There is another question in the chat space, perhaps before we proceed. And
All right.
let me read it. It's from Praise Faraha. It says, from your experience, what extraction method has proven most effective for isolating lignin from agricultural biomass like rice husk or banana peels? And what makes it scalable for industry ready? The other statement with a question is, removing lignin usually means using strong chemicals and creating a lot of toxic waste, which harms the environment. What
Right.
are proven ways of tackling this?
All right. Thank you so very much. In our effort to make the production process to be clean as possible, we have in our society today where a lot of people that are using firewood as fuel generates ash. And this ash material, wood ash, cornstalk ash, and rice after they are burned to take up the carbon in it in form of to generate the energy, the leftover is ash. And this ash, we know from elementary chemistry, we've got this ash are rich in alkaline and alkaline earth metals, potassium, sodium, calcium, magnesium, and what have you. Right. So from there, we carry out the leaching. And this leaching will leach out these inorganic materials. These are alkaline earth metals. And after leaching them out, instead, generally or traditionally, lignin extractions are done using alkaline, either steam explosion or ammonia, to be able to break down the bond and then to release the what? Selectively to release the lignin. In our own way, we try to, by all means, to be able to like reduce the chemical footprint of our. Okay. Hello. You there? Hello.
Yes, yes, we have muted him.
Great. Okay. So what I was saying is this: we try to make sure that whatever we are doing it's done in a sustainable manner. So wood ash leachate, we use wood ash leachate to be able to selectively remove the lignin from biomass. And that we have optimized the process, and that's what we're doing. In fact, there are 3 different scenarios that we have demonstrated in the lab. Number 1, to be able to use the sodium hydroxide as the basis, and also to use lignin, the leachate, wood ash leachate as one of the scenarios. And then the third one is to see within 1 molar of 0.5 molar combined with wood ash leachate to be able to see what are the efficiency of the lignin extraction from the biomass. And this we have done, and that has been demonstrated to be demonstrated to see that wood ash leachate can actually be used to replace the chemicals, which is sodium hydroxide, that are generally utilized in the lignin extraction. So that's in our own method, we utilize wood ash leachate. That is part of what resource recovery from waste. Thank you so very much. Hello.
Yes, we can.
All right. Thank
Yeah.
you. Hello.
Yeah, with you.
Yes. I see Praise reacting with a claps up emoji. That means the response was satisfactory to his inquiry. Maybe just a last one on the ignition.
Right.
You did make mention of the fact that one standout characteristic of these cook stoves is that they have an aspect of self-ignition.
Right.
Perhaps you would explain the mechanism of the self-ignition, because back here in Uganda, we have to again get some paper, and then you have to light, these briquettes in order for them to
That's
fire.
correct.
Perhaps you explain that.
Yes. All right. As I earlier stated, while the cooking is in progress, energy is being stored. Prior to that, the system is also as it's equipped with what you call the energy storage pack, which is energy storage device, which is the battery. Okay, battery packs you can see here. These batteries are charged from the energy from the tank and from the small turbine, okay, steam turbine underneath. Now, in the case of you want to start the new cooking, what you need to do, this energy storage there is now used to supply the igniter. And this igniter will be light up in situ while the fuel is already loaded. Yeah, so and there's the button here. If you look at this particular, right? Are you still seeing my slide?
Not yet.
Okay, let me share it more. Yeah.
Please reshare. Consider sharing the screen. We can't see.
All right, I will do that again.
Yeah. Bashir, please mute.
Okay, so you can see it now, right? Can you see this?
Yes, we can see.
Yeah.
We can see it.
Here, this particular, if you look at here, Can you see here, red button here? Can you see a knob here? If it's not that clear, let me expand it, I think. Can you see this now? Can you see something here?
Yes.
Can you see? Here.
Yes, sir.
Very
Yeah.
well. Okay, so when you look at what happened here, this is the control button. Before we start, when we load the fuel here on top of this, we've got to on this, and by the time we on it, the energy that's already in the system will now be able to light up this particular. Okay, let me see if I can have a very better view here, but it's not. Let me see if I can, because of before I leave this presentation, I'll get another picture so that you see the top view clearly where the igniter is all about, is situated. So by the time we on this, the igniter will just light up, and then you've got to see the okay, one sec. We got to see the how it is self-ignited, and then the fuel will begin to undergo combustion gradually. So this is the mechanism we have utilized based on the energy it has stored in the battery. In the first place, during the commissioning, you just need to have your battery charged, and that's it. Any other subsequently, no need. It will be charging itself while the cooking is going on, and you can discharge by also tapping, by using it as what do you call for another electric supply or electricity supply in a room. In fact, if you burn a kg of coal with this our system, you can generate up to you can light up to what you call 20 bulbs of within 5 to 10 watts. So with this 1 kg, you can, in fact, while you're cooking, you can light up your house, and then everybody's happy. And so this is what they're all about, this solution. Yeah. Okay. Let me see if I can get the picture more.
Very much okay. I do see another hand, so I would let him ask this question directly while you're trying to grab the next picture.
Very
So,
well. Yes.
Abdul Rahim.
Okay. Hello, can you hear me?
Very well. Loud and clear.
Thank you, sir, for the insightful presentation. It's always an honor to learn from you again. So I'm curious, I don't know how scalable is this greenfuel technology for industrial application, like maybe in Nigeria. Thank you.
Yeah, very, very scalable because, okay, thank you very much for this question. Yeah. So this technology is scalable, and we have demonstrated some people have approached us within the federal government of Nigeria, and we've like supplied them with what we call how to put it, initial piece, and then for them to give us the feedback so that we can improve on it. Now, what the stage we are in now is to do what we call commercial production. So re-engineering of the entire system is nearly into completion. And the one good thing is this, the administration of the university are keen and very interested in this particular project. And we've had some like couple of 2 or 3 presentation to federal government agency who are we are in touch with them, and hopefully very soon the product can be launched into market, and then we begin to mass produce. So the issue of scalability is very scalable, and we have different solutions for different people. We have solution for people, the restaurants. We have solution for personal house use. So these are the things we have tested, and then can be scaled into. In fact, the scalability is not an issue that has been. We have gone back past that particular level. Thank you.
That's really interesting, sir. Thank you very much for the response.
Great. Okay. Yeah, questions, please. We have questions asked, even if it's outside this presentation, please.
Okay, Doctor, could you draw a comparison on using biomass precursors and plastic precursors for energy fuel production? What are some of the advantages and disadvantages of using both?
Perfect. Okay, so plastics and biomass, they have different energy density. Okay, so plastics, you're using plastic as a energy precursor. What by so doing, we invoke the process of pyrolysis to be able to liquefy it. And after liquefying it, you've got hydrocarbon-rich component, because the plastics more often have got originated from either basic all these PPs, that is PPE, polypropylene, PATE, polyethylene terephthalate. We have ethylene, so many things, because which are what fundamentally hydrocarbon in nature. All right, so the energy density is quite higher compared to the biomass, which contain carbon, hydrogen, and oxygen. And then the more oxygen you've got in the system, the lower the energy content. So this is those are one of the disadvantages. So what we're trying to do, or what we are doing in material energy laboratory, is to do co-firing, either pyrolyzing the biomass together with the plastic, and then to generate high, what you call liquid product that is rich in high hydrocarbon content with low amount of oxygen. And one of our additional thing is before you can achieve that, the melting point of plastics can definitely affect the entire production process. So what you need to be ensured is for this entire system to be at thermal equilibrium. At no point that the plastics before the condensation unit will tend to go into solidification. But if that happens, there's going to be a build-up, and you are likely to see what you call burnout within the system. So to avoid that, you must bring the biomass to the near energy density as the plastic works together, so that the energy density disparity between the plastic and biomass could be reduced significantly. How do you achieve this? To densify the biomass is to either torrefy it or to generate hydrochar, and then mix it with the plastic, co-fire it via pyrolysis, and you got to generate what you call high liquid rich in high hydrocarbon content, which can further be fractionated into light ends, middle distillates, and also heavy bottom. And this heavy bottom can also be blended with the bitumen, and can be applied in sustainable infrastructure, for example, in the road construction. And then the middle distillate can serve as fuel, or as substitute, or a blend can be blended with what they call the AGU, automotive gas oil, or biodiesel, to serve as another fuel. While the light end, which can be also used as a biogasoline, it can be used in different applications. That also has been demonstrated in material energy laboratory. Thank you so very much.
Wow. Wow. That is great. That is impressive. I just had to react immediately. That's really impressive to hear that. Thank you so much for sharing, Doctor. And I want to encourage everyone, if you have a question, I think you can go ahead to raise your hand directly and have one-on-one discussion with Doctor. Okay, this is the top view.
Right.
So
let's have a look.
yes.
The system has the capacity or capabilities to allow fast cooking or slow cooking. So for slow cooking, we operate under natural draft. But for fast cooking, depending on the intended user application. So now we want to demonstrate how fast cooking can be effected. We have a button that regulates that, and then that will be set in now. Let's go. See, the glowing has increased considerably. So with this, you can regulate it depending on the the user intention. So if you need fast cooking, this can also be affected. So this is one of the advantages of this system compared to the local one, in which you don't have control. You don't have the flexibility of controlling the cooking rate. Yeah, so this is it. Thank you very much. So if you look carefully, there is, you can see here, you see the white something here? Can you see that?
Yes.
Yeah, that is the igniter. That is igniter. That ignites the fuel, okay? So this is the top view of the stove. You can see the biofuel stove, and so this is what we have currently operating in the lab. Thank you.
And I have a question.
Please
So
go ahead.
the igniter, right, is the same mechanism with spark ignition engines, like when you have the
That's perfect. Yes, exactly. So when you on it, using the energy stored in the system, it's now become very much. Now you've got this. If you look at this, I hope you are at least seeing my slide, is it?
Yes.
You see this brown briquette here. This brown briquette will be the first point of contact, and then it fires up and then light up the remaining what do you call the coal within the chamber, and then you are good to go. And so that's the system we have developed so far.
Wow.
Yeah.
Well, that's perfect. I do want to mention to everybody, we have a survey in the chat box. Please help us to know what you enjoyed about this particular section. And if you've been joining us previously, we want to hear your feedback. We want to hear what you think about our webinars, and also what more topics do you want us to bring to you. And I want to kick it up with some of the questions I had written during the course of your presentation, Doctor. I do have my first question, which is regarding the amount of biocoal that you produce from each of the process, because I heard you mentioned that 1 kg of biocoal can already power 20 bulbs. So I was then wondering, what is the total amount of production that you can achieve in a day or like per process?
Very well. Thank you so very much. This has to do with the facilities you have on ground. But if you process, let's say, for example, you've got for 1 kg of biomass, yeah, from the starting point to the end, you're likely to get about 70% of that to be converted to biocoal. 1 kg, you're likely to get 700 grams. So that's it. From 1,000 grams, which is 1 kg, you will likely to get 700 grams of what? Coal. So it depends on your production capacity. If your system allows, particularly the briquetting machine. So if your briquetting machine can produce 60 briquettes per second, or per minute rather, then you can produce at least up to 10 tons in a day. Yeah, so that's doable. So more questions, please.
Yes, there are some questions in the chat box. I'll allow our moderator ask them. Enoch?
All right. I was still enjoying the responses. All right. We have, I'll start with the last question from Praise, and then I'll move forward. So Praise, as always, has brilliant questions. This one is, what types of plastics are most suitable for energy recovery? And are there specific plastics that should never be used in these processes? Yes, we'll respond to that. Then we have another one from Clinton. Yes, awesome. Doctor, over to you.
Yeah, thank you so very much. We have some plastic that's thermosets and thermoplastics, is it? So thermosets are just these plastics that you see you can, when been degraded, they cannot be recycled any longer. Whereby is thermoplastics, which are what the polyethylene, polypropylene, what do you call them? This normal packaging, food packaging material, we use polystyrene. Yeah. So mostly we channel polystyrene to different routes, but polypropylene, polystyrene, also PEX, also to another what do you call material stream. So the PPs is what we are interested in converting into liquid fuel. Well, the other polyethylene terephthalate and also the other plastics, what we use them for, we try to like polyethylene terephthalate, we try to get what pegs out of them, peg polyethylene glycol, and the polyethylene glycol, which we try to convert it to what you call to generate what you call hydrogels, which can be used in the what do you call for agriculture to be able to release water as at when needed when the drought set in or in a situation whereby in areas where the rainfall is not that much, so we can develop this hydrogel from the pets so that in addition to using the lignin from biomass as cross linkers so that we get the hydrogel produced to support agriculture and which in turn will support food security, and particularly in sub-Saharan countries and also in the desert-prone areas where rainfall is very minimal. So that is one stream entirely. The polyethylene, polypropylene, those ones are suitable candidates that can be mixed blend with biomass to generate high-grade fuel via pyrolysis. While the other what do you call polystyrene, we don't subject it to this process, but we tend to produce some graphene out of it because styrene is a multiple graphene is a multiple component or structure of what you call styrene put together. Then polystyrene, which is what benzene, isn't it? So by the time we seize the ethyl group out of it by subjecting to what synfree, and then that ethyl group is burned off, and then you have the what benzene ring put together, and that gives you, by the time you subject to thermal processes, you're going to get what you're going to get at the end of the day, you get your what the components that are very, very strong, that are very light, but have a strong, what do you call, material property that can be used either in building construction or in other applications. So this is where we channel our what steering to polystyrene, plastic waste to, and then the PPs fuel, and also the PETs into hydrogen production. So these are different because when you have a cocktail of plastic, this is one of the challenges that the plastic industries are facing. And we also have come in a situation whereby you have in the plastic recycling business, there are challenges in terms of sorting, and that is the stage that requires a lot of energy, and also the downtime is highly experienced in this particular stage. So what we say, okay, fine, let's come up with a system that no matter what the plastic waste constitute, we can be able to segregate them into either HD or LD, low density, high density. And that we have successfully demonstrated, and then that has been looked into to get the IP so that we can solve about more than 30% of the waste that is generated in plastic recycling companies, that can be able to what do you call, eliminate that. And then what gets into the plastic recycling companies will be the feedstock, not longer raw material, and that will also improve their return on investment and the daily earnings, and also make the plastic recycling systems more so to say more sustainable. Yeah, so those are the things.
Wow. A colleague of mine sent me a message and they're like, the chemistry had benzene rings and etc. I think
Yes.
that responds to your question in depth, Mr. Praise. So we have a brilliant one from Clinton, thank God, and he says, thank you for this informative presentation, sir. I would like to inquire about the cost effectiveness and accessibility of this solution for low-income demographics, given that the primary target market appears to be rural communities with high fuel cooking demands. So his question is about cost effectiveness and accessibility to low-income demographics.
Very good. Okay, now look at this. Our raw materials waste. Okay, our raw material is from waste, biomass, right? You can get it at a very, very cheap price. In fact, there are some instances, this pile up of waste, if you go there, you just negotiate with them. Okay, I'm going to be packing this for you. You pay me for collecting your waste. While you're doing that, you process your waste and get additional pay. That's one. Raw material is completely nearly zero waste. The only thing is the logistics. That's number one. Number two, you've got also the chemicals that that you're going to use as a binder to produce your binder is also derived from waste. What we call it, the wood ash. Wood ash, you just carry out leachate, and then you've got the leachate, and then that serves instead of chemicals they utilize, you now use resource recovered what do you call a chemical or solvent, and then you selectively extract your lignin as a binder. Now, what happens is what to be able to torrefaction. Torrefaction, you need heat to be able to carry out that. Now we have solution for rural areas which are not what connected to what either grids and what have you. They have no source of electricity. We have um, what do you call biomass fired pyrolysis system. That system, the technology we use in that the design. If you look at this, let me show you. There's one picture at the background so that you understand what I'm talking about. I say 1 second. Yeah, have a look at this clearly. Okay, look at this behind this top. You see a lag system here. Do you see that? This very one.
Yes, sir.
Yeah, with handle like this, right? That is the solution for rural areas that are not connected. In this system, we utilize this concept of what rocket stove, where we charge in biomass within a concentric cylinders, and then we also fire it using biomass. So as the process progresses, it generates what you call light ends, which are combustible, and then the system has a returning pipe that will make the system to be what sustainable. So after the torrefaction, the system, when there is no more what do you call production of what the light volatiles again, so the system has reached completion, then you allow it to cool down, then you dismantle, you have a what torrefied biomass, and that's you have completely more than 50% is what cut off. You don't need additional energy. System is so self-sustained. So the where you've got an issue, or probably you've got to have energy input, is to be able to bring out the solar system to power the what combination stage. That is to be able to pulverize this torrefied biomass and be able to blend it and also to carry out briquetting. So these are the where you have where the energy requirement, which can also be satisfied using clean energy such as solar. So this is, and then if you compare to the traditional method that is being used in producing briquette, you could say that most of the briquetting machines we have in our society nowadays, they are based on three-phase because the barrel need to be heated up to a certain temperature to be able to what produce the desired briquette. But ours, it's not the case. Ours, we try to see that we cut down anything that is energy intensive, and then we that can also be what you can also utilize the green energy, particularly solar, to be able to effect all this transformation. So this is it. The cost implicate. This is very, very, very. In fact, in fact, we did some sort of what you call pitching at Innovation Hub, and our call for packaging goes for like 160 naira. I hope if you can convert that to another what do you call currency, 160 naira. As at today, 1 kg of biocoal, the traditional biocoal in the market is more than 500 naira. So the economics are very, very, very interesting, that you can see that when we launch this product into the market, I believe it's a game changer, and everybody will have to go away from that bad fuel that is costing very high to a very clean fuel that with less cost, that is environmental friendly. In fact, we have a solution for the big shot. You see, these big shots, the people that handle the kitchen wouldn't want to see their wives, looking dirty with the coal. With our solution, the coal is coated such a way that it doesn't stain, and then that's why you see it is shiny. And we coat it with what? The lignin. So this is one of the uniqueness of our product. And all these things are 70% from waste, nothing from waste. We use the production is based on the principle of circular economy. So that everything you see, any stream from the production process is utilized in another phase. So this is one of the things I can assure you. I tell you for free, this is most what you call interesting business. You injecting 1 million naira, I can tell you, you can have triple or quadruple of that within the return of your investment. And this is clear. This has been demonstrated. This is very, very clear. The market is there. This is what we call market-driven innovation. It is there, the market is there waiting for the product, not you. So that tells you that less of what marketing will be needed. By the time you saturate the local communities, you've got everything, everybody, you've got the politicians buy in, and you are done. You just be supplying this product into the market, and then the demand will be so very massive. That's what we're taking our time. By the time we launch we hopefully to launch this by the end of this year, and then our product will hit market massively, and then that will be the game changer in terms of satisfying domestic energy system, while also decarbonizing the domestic heating system. Thank you. Hello.
Yes. Wow, Prof. At this moment, I feel like asking for money, like to draw investors to this
Please.
company right away.
That's great.
Like you've convinced all of us. Like at this moment, if we said let's crowdfund for this project, everyone would be putting in their money right now to make this happen, because this is a game changer. You talked about circularity, the idea of reusing, reintegrating every waste, and it's just amazing. It touches upon everything about sustainability, using renewable sources, circularity. So I'm blown away by this presentation. Thank you so much, Doctor. I do see there are questions um that have been asked before the questions at the down part. So I will try to take some of them that were asked previously. So there was this question on just a moment about, okay, the lagging issues. I think maybe you have touched upon that, because this is from Thomas. He said, greenfield revolution is very essential in our contemporary world, but what are the lagging issues or reasons why government hasn't implemented all of these for mankind? I think you've already mentioned that the technology is just it's ready already, and you've piloted some of this technology with the government. So I believe that the answer is coming. Like we're hoping this year. This is launching Nigeria.
Yes, yes.
Okay.
So let me just throw more light on that. It's a lagging insulation, isn't it? If I got the question right, is it lagging? I don't understand what that means.
So I would want to know about the insulation, but actually the lagging he used here was more of the reasons why there's a delay in the implementation of the solution. Yes. But you did raise a very important concept that I would like to
that will be next time. I keep that for now.
Okay. I think the next question will want me to make my announcement, will lead to my announcement. So someone is asking if an undergraduate from another institution can join your lab for an internship. So
Very well.
from
Very well. Before you land, very well. Free. Welcome.
Yes. So I wanted to also build on that. So look out for this year. We'll be launching a collaborative fellowship where Renewable Technologies will be working alongside the Materials and Energy Laboratory that is spearheaded by Dr. Isah Yakub Mohammad. And what the fellowship will be all about will provide you theoretical understanding of the different renewable energy systems, including the biofuels, and then you would have a follow-up with an internship physically at the Materials and Energy Laboratory. So if this is important to you, and in fact, we are driving this more than just looking at those in Nigeria, we are also trying to see how we can collaborate with other companies in other countries to also facilitate the internship component of the fellowship. So please, we would start with Bauchi State. So if you're a student at the Abubakar Tafawa Balewa University, so please send us an email right away. Send us an email. I'll put our email in the chat box. It's renewwats, triple T's at gmail.com. Send us an email. You will be the first people would be considering for this amazing opportunity because you attended this section. And so please send us an email and then we will take up the discussion from there. But Doctor, there are more questions in the chat box because
No problem. Keep them coming.
Because, like Grace rightfully mentioned, that more explanations are sparking more questions, and truly we are loving it all. So he said he is asking about the lignin extraction.
Right.
So he said, concerning your experience with lignin extraction, when it comes to the resident time for the leaching process, for leaching, is the wood ash solvent more effective compared to treating it with chemicals? Okay, so it's comparing it with, you mentioned sodium hydroxide as the conventional solvent, and now you're using wood ash leachate as your innovative components.
Right. That's correct. Absolutely correct. So what we do when you have the first cycle of wood ash leachate, there are things we check. We check the pH. We check also the electrical conductivity. So when we apply it and we see that in comparison with the sodium hydroxide, the yield is around 50% compared to that sodium hydroxide. Then what we did was to be able to reconcentrate the leachate to have more of what you call ionic component in the solvent. And when we concentrate that is to remove a lot of water out of it. That is the water that is used as solvent during the leaching of the wood ash. So when we concentrate that, we apply it and see that there is a great improvement, nearly 70%. We cannot achieve 100% at this point, but unless we continue to intensify the process so that to the extent that we optimize the process variable put together, and so that we can be able to achieve nearly, but I am not sure that we can have 100% as sodium hydroxide. That I'm not too sure. But at the moment, we have reached up to 70% in comparison with using sodium hydroxide. That's the situation at the moment.
Thank you so much. Thank you so much. And I see a lot of people campaigning to come to Nigeria now. And a lot of people wanting to transfer to Bauchi State at the moment. Yes. Please go ahead and also fill in our survey and tell us all of these things that you are sharing with us right away. Fill in the survey is in the chat box. And there's an interesting question, and I was waiting for this, and maybe I'll give permission to Brian to speak, because they currently won a competition where they designed a hydrogel solar evaporator. So when you mention hydrogel in your process, one of the products, I was waiting for them to ask a question. So Brian, you can unmute and ask a question directly.
Am I audible?
Yes.
Thanks so much for the invite, Madam Shalom. When I had the doctor spoke about hydrogel, I said today is the best day of my life. I would like Doctor just to help us throw more light about the hydrogel because I talk about the water release and our design was about the water purification using hydrogel. And I believe it will be of more system to us in how it's working on this hydrogel, how it's making the synthesis. Yeah.
Okay. Thank you so very much. Yeah, as I said, PET, polyethylene terephthalate. What we do is to produce the PEG, which is one of the feedstocks that's required to form the what we call to produce the hydrogel. So when we get the PEG, we do subject it to size reduction, and then after that we do what we call extraction, so that we've got the liquid. And that liquid, we use some chemicals to be able to like selectively remove the PEG, polyethylene glycol. And the polyethylene glycol will now serve, in addition to crosslinker, the lignin, also put together to form under certain condition to be able to generate the hydrogel. And this hydrogel in our focus is for agricultural purposes, to be able to release water as it went due to the plants, particularly in drought-prone areas where the rainfall is very limited and what have you. So this at the moment, this is what we are doing. The process intensification of this particular technology is still on the way, and by the time we come to conclusion, having optimized every parameter, that the details, full details, will be shared with the wider audience. So, but at the moment, this is what we are doing in the Material Energy Laboratory, to be able to convert these PEGs into PEGs, and the PEGs together with crosslinker, which basically is the lignin, and to form a hydrogel. This is what we have at the moment.
Great. I would welcome back our moderator. Enoch, do you see any more questions in the chat box? And I would also want to ask Dr. Isah. I know students at Goodwill University, they are very brilliant people. A lot of them are on the call right now, and they were asking if I could share your email address with them for some consulting. They are particularly brilliant. They've done a lot of work, even in biogas. So a lot of them are here, and they are just amazed by your presentation. I would just want more discussions and more opportunities with you. So I wanted to know if that is okay.
That is very okay. Very okay.
Okay.
You can share my email. Yeah, that's fine.
All right. So Enoch, are there more questions in the chat box that Doctor needs to attend to?
I think there is a question that let me just pull it up. It was about from Thomas Sandy. He says, "Thank you so much, Prof. Green fuel revolution is very essential in our contemporary world, especially in Nigeria. What are the lagging issues or reasons why government hasn't implemented all this for the benefit of man?" This seems more like policy, but yeah, I believe Doctor can take it on.
Yeah, I think this question was asked earlier on. Yeah, and
Yeah.
then okay. Generally, why government are not too keen about adopting this is, how do I put it, is the push. The push, if the push with evidence, you can get government involved in it, and one very important point is to have the right contact. We've got the right contact within the government, and that's you you approach them because generally of a typical African setting, you need to push things by yourself. So when you have this kind of solution, and you don't expect people to come, because there are competitors who are also working on this. For your solution to fly, you need to push push to the point that they will have to come to you, and so that you now you push to get the attention, and when that is achieved, you are good to go. Demonstrate it. There's an initial commitment. For example, you need to make some of the solution free to people. Let them try it and get the feedback. By the time they try it, one person try and they communicate to 10 people, you can see the what awareness is going to be geometrical. So by so doing, you get a lot of people buy into your solution, and then that will be the game changer. So unless and until you approach the government, you approach the right contact persons within the government to be able to see exactly what you're doing, the value and the knowledge you are sharing, the transformation, number of people you are living out of poverty because of this solution. You talk with numbers, with evidence, and I tell you, you are good to go.
True. That's really true. That's true. Okay. I think there are no other questions in the chat box. Please, can we turn on our cameras if you're in a very comfortable place? We would like to take a picture with our prof. And okay, there's one final question here from Hashim. They just asked if you're open to market your product in other countries. I assume this is from our students in Uganda.
No problem. Yeah, when we after launching the entire, I mean, after
In
the five
Nigeria.
months, yeah, within the year, I think it's fine. We can collaborate so that you can be maybe about the coal and the stove. We can be well. We'll look at it, the terms, and then so that every party is happy. And then Uganda, you begin to see smokeless and ashless coal from Nigeria, and that will spark the further collaboration with the government of Uganda and Nigeria, and then everybody will be happy, and the African countries will now be a better place to live in. With the syndrome of Japa will now die naturally, and then we make Africa great again.
Well, I know it's not a target to me because I believe we are
You will come back to the country. You come,
we will
coming back to
I'm
Nigeria.
coming back to the country. I
Yes.
have to.
Yes, we come and contribute. Yeah, it is very important
Okay.
we contribute to
Yes, definitely.
yeah,
Definitely.
right.
I know one person just asked about patents. If you from his profile, he has 3 patents already, and I feel like more is coming.
Very well, yeah. We got patent for the biofuel. We got the patent for this self-ignition stuff, and then
Mhm.
we're also into materials, as the name implies, material energy laboratory. We have also have a patent for a green pathway for barite beneficiation. Yeah, because our barite is one
Wow.
of the minerals in Nigeria that this oil and gas industries, particularly Shell, Chevron, they normally what you call source it out from the abroad, from outside the country, which cause a lot of what you call the exchange rate depletion of our foreign currencies and the dollars in
Mhm.
the dollar reserve, and that has a negative impact on the economy. So we're like, okay, what is the problem? And when we approached them, they said there are no what you call standard protocol for producing the barite that meets the industrial benchmark. I said, okay, we can do that for you. And they said, okay, give us the down. Okay, then they said we should go ahead. And then suddenly there was this call from a Nigeria Tertiary Education Trust Fund called TED Fund. The call, we put up what do you call a proposal, a concept note. It was accepted, and then followed by a proposal. Then we got the grant, and we get the grant running. And as I can tell you, we have been able to beneficiate any type of barite, raw crude barite, the mineral deposit, bring it to the material energy laboratory, be it one SG of 2 points, less than 4%, we can be able to give you barite that is beneficial using the green pathway into what you call SG of 4 point and above, which is the industrial benchmark that we have successfully established, and we have patent what do you call that particular technology is fully green. Nothing, no chemical, nothing. Yeah.
Wow, that's impressive, super impressive. Thank you so much, Dr. Enoch, I'd like you to appreciate the pictures. And Doctor, maybe if you can stop sharing your screen so we can then see everybody on
Right. Okay.
the call.
Okay.
All right. Just like Shalom echoed, if you're in a comfortable place, would really like to see your beautiful, handsome face in our pictures. Because we are going to, we are going to go wild on LinkedIn. So ensure that your smile is okay. Brian, make sure you smile. All right. So 3, 2, 1. I'm going to take quite a number of them, so please don't get tired. So the next one, shortly. All right, let me also smile. Renew what's. All right, the last one. Okay, so thank you very much for joining in, and I'm very excited that we have learned a lot, particularly from Doctor as far as biomass conversion is concerned. I think as Gul University, we have been doing something related to clean cooking, but I think after the detailed presentation, we are going to have to rethink how we are doing it, because how can our friends from the West have these very brilliant ideas? For me particularly, I'm seeing a potential final year project from just this webinar. I'm going to have to rewatch it and try to coin something. So, and I know these are, the testimonies from very many of us that have joined. We are very active as Renewers on our social media platforms, that is particularly LinkedIn. In case you've not yet followed us, please do. We also have a YouTube page where we do well to post the recordings for these sessions. And I want to encourage you to go and review the recording for this session, because there was that moment where Dr. Rich Tani was speaking hardcore chemistry, benzene rings. Oh my goodness. I had to record some O-level chemistry. So please check out our recording. It will be uploaded on YouTube. From us to you, we really love you. And we look forward to the July edition. Please like our posts. Always. Thank you. Shalom, over to
Yes.
you.
I want to end with a survey. The survey, please let's not forget the surveys. It's in the chat box. Please fill it. And the students from Bauchi, I saw a couple of you. You introduced yourself. Please send us an email immediately after this section. We would love to continue the conversation with you. So please send us an email and please fill out our survey. Thank you so much. And thank you so much, Doctor. It's always a pleasure talking to you. I still don't know how to appreciate you for the time. It's amazing. Thank you so much for the valuable information. And let's all keep looking out, because Doctor has mentioned that he would love to do a practical section. So keep on the lookout. We would set up this section again where he would practically demonstrate some of the things that he has talked about today. So do have to follow us via LinkedIn and all our social media pages, like Enoch had rightfully mentioned, and look forward to the emails from us. So thank you so much, everyone, for joining. Thank you, and have a great day. Thank you so much, Doctor. It was a great privilege for us. Thank you so much.
Bye-bye.
Thank you so much, everyone. Remember our survey and let us know. You can send us messages if there are things that you want us to discuss about later on. Please send us emails of topics that you want to see, practicals that you would love to experience, and we'll try to see how some of those things could be set up. So thank you so much. Thank you for joining. Have a great day.